Hey folks, I'm Mr. Hartzler and I want to talk to you about graphing polynomial functions. So let's get started. I know this looks like a lot of vocabulary, and it is, but a lot of it is pretty intuitive. So as we go, we're going to kind of talk about this. But in general, they're all right there. You can freeze the screen or pause, whatever you want to call it, and go ahead and take some notes on that if that's something you're interested in. But the main target here is that you can predict the behavior of polynomial functions. Let's get started with an example. So how can you write a polynomial in standard form and use it to identify the key features? So let's start off with the leading coefficient. The leading coefficient is going to come from whichever term has the highest exponent. So let's do numbers of terms first. The terms are each separated by their plus signs or minus signs. So this is a term, and this, and this, and this. So there are 4 terms in this one. Over here I have 1, 2, 3, 4 things again, so another 4. Leading coefficients. Now this one again, it comes from your term with the highest degree x, the highest exponent. So which of these 4 things have the largest exponent? Well, x to the 5th is the largest exponent, and so my leading coefficient is the number in front, and that actually was a positive, so it's going to be a positive 6. Now this other one over here, which one has the largest exponent? Well, it's this one with the 8. So then what is the number in front? What coefficient or number in front is it? It's a 7, positive 7. Then I need to look at my degree. That comes from the biggest exponent on the x value, not on the other stuff here. So all of these, let's see, there's actually x to the 0 here, because anything to the 0 power is 1. So there's x to the 0 there, and then 1, 5, and 2. So 5 is my largest exponent on x. And over here, it comes from 8. All right, let's go on and look at another example. Okay, this looks like a table. There's a lot of stuff here. Each of these are going to be a little bit different. So I have an odd degree. So it means an odd exponent on my largest part. So something like x to the 3rd plus x squared plus 3. Okay, something like this would be an example of that. And that's because my largest exponent, is an odd number and a positive leading coefficient. So that means the number in front of this x cubed is positive, which in this case it is. It's positive 1. My end behavior, so just what the last part of my graph is going to do in the very first part of my graph. If it's odd, that's weird, right? So I'm thinking opposite directions. Things are awkward, it's weird, like I wouldn't walk around the hall like that. So I'm going to have positive. That tells me what's going on the right side of my graph. It could do a whole bunch of stuff in the middle. I don't worry about that right now. But then I do need to look at the left side of my graph, and it's going in opposite directions because it's an odd number. I like to think about this like the number 1, if I draw it normal, the number 1 goes up and down, so they go in opposite directions. Even degree, they're going in the same direction. So let's look at this even degree positive leading coefficient. So that's something like x to the 4th plus 3x squared plus x, something like that. So even degree, because my largest exponent's a 4, positive leading coefficient, let's throw a plus 4 in front of it. So that means that I have an even degree and a positive leading coefficient. Both of my sides are going to go up. And this is just like a parabola. Remember, a parabola falls under this set of rules. So like x squared equals y. I know what that graph is, right? That's a simple parabola. I'm doing this way at the tippity top of the paper, or the screen if you notice there. Both sides go in the same direction. So that's what this is going to do. I don't know about the middle, right? There's a whole lot of other stuff there that we're not to yet. But for right now, we don't care about the middle, just the ends. Now, let's look at odd degree. So again, something like maybe x to the 5th plus a bunch of other stuff. As long as x to the 5th is the biggest one, we're good. And that's a negative leading coefficient. So something like a negative 3, or let's put a 2 there, just so you don't think that that has to be an odd number as well. So like a negative 2 in front. It's an odd exponent, that 5 there. So that just means that they're still going in opposite directions, but the right side, because this is negative, it's going to go down. All of my leading coefficients, they tell me what the right side of my graph is going to do. Then I look at my degree to see what the left side is going to do. And since they're odd, they have to go in opposite directions, so my left side goes up. Over here, we're looking at even degree, so something like x to the 16th plus x to the 15th, something like that. But again, negative leading coefficient, so we'll do a negative 3. Because it's an even degree, I know they're both going to go in the same direction. The negative leading coefficient, that means my right side must go down, because it's negative, down. And because it's an even degree, they both must go in the same direction, so my left side also goes down. You could think about this too like a negative x squared. That parabola opens down, if that helps you. Let's go on to the next example. All right, so now we're on to this example. I filled in this table for you, but we're really just going to consider this polynomial function here, and we're going to use a table to kind of learn some things about it. So I would take each of these numbers and I'd plug them into that, and I'd see what my y value ends up being. We're going to do this for number 1 because that one's just the easier one. I want to save us some time. So f of 1 is 1 then to the 5th plus 12 times 1 squared plus 8 times 1 minus 3. So 1 to the 5th and 1 squared, there's still just 1. So this is 1 plus 12 times 1 is just 12 plus 8 minus 3. 8 and 12 is 20, and then 21 minus my 3, so it gets me 18. I'm going to clear all of this for us real quick. So now let us talk a little bit about whether a function is increasing or decreasing and some turning points here. So I'm going to actually plot these on a graph, just lickety split. All right, so now we've graphed all of those points, and I can even connect these and kind of get a rough sketch of what this graph might look like. But I really need to pay attention to my end behavior too. So my leading term here, these are in descending order, so it goes largest exponent then down to the smallest. So that means right here I've got an odd degree. My degree is odd, so that means my end behavior, they're going to go in opposite directions. My leading coefficient is a positive 1. So that means the right side is going to go up. So that means, again, I know it's odd, so they're going in opposite directions. So my left side goes down. Then I can kind of connect these dots. Real rough, but you get the idea. So looking at my graph and looking at this table, I'm negative and I increase. I'm going up to 0. So from here to here, I'm increasing, right? If I am increasing and then I start going down again, I went from negative 3 to 0 back to down to negative 3. So I'm increasing and then I decrease. So this is a turning point. I can see that in my graph too. I'm going up and then I turn and I start going back down. And then here at this 0 to negative 3, I went down, I decreased, and then I started going up. I ended up at 18. So in there again, somewhere between 0 and 1 is another turning point. You can look at the definitions at the beginning, but a turning point is when I go from increasing to decreasing or decreasing to increasing. So that's just something to keep in mind. Let's see here. Another important piece, we have a relative maximum right here. A relative max. Relative max is not an absolute maximum. It's just one that's maximum relative to the stuff around it. So if you notice a little bit to the left of that dot and a little bit to the right of the dot, it's down. So that means that if you look at its neighbors, this spot is the highest if he looks left and right. So down here, this dot, that is a relative min. And that's because if she looks left or right, she's the lowest on that in that area. So that means relative minimum. An absolute minimum would be somewhere like this, where there's absolutely 0 coordinate points that go lower than that. We don't have it because this chunk here goes negative forever, and this piece up here goes positive forever. So I'm not going to have an absolute min or an absolute max. Instead, this example over here would, but I just realized you can't see the stuff I wrote. Anyway, this dot here that I'm pointing to, that's the relative minimum. And that's kind of all of our points there. We also have a couple of x-intercepts. So here, from negative 3 to 18 on my y-axis, if my y is a negative and then later it's positive, it means somewhere in there there's an x-intercept. So somewhere between 0 and 1, I cross my x-axis. An x-intercept somewhere in there. And I actually know exactly where this one is because it's at that point, right? Negative 1, 0. That is an x-intercept right there. So that's kind of nice. Alrighty, and let us go on to the next example. Alrighty, so now I need to take all of this information and I need to put it onto my graph. And I'm starting off with positives. This is where at the beginning of the year it's important to know what things are positive, negative, that kind of stuff. So positive from -2 to -1. This is an interval, not a coordinate point. And it's parentheses just because we're not including those spots. So I'm positive from -2 here to -1, which means I must be above my graph. And also from 1 to 2, which is here to here. I'm positive there. Then the function f of x is negative on the intervals -∞ to -2. So that means this way, right? I'm negative below my x-axis from this -2 all the way to -∞, or you read it like there, -∞ all the way up to the -2. Then from -1 to 1, -1 to 1, I'm also negative, and then 2 to infinity. So here to infinity. Now I need to go in and make sure I'm a little bit more particular about some of these. Usually it kind of shakes out okay just from that information, but we need to be a little bit better here. I'm increasing from -∞ to -1.5. So right about there, I need to make sure I'm going up that whole time, which, like I said, it's pretty accurate there. Then from 0 to 1.5, so from here to here, I'm increasing, good. And then I'm decreasing on the other chunks. So here to here, I'm decreasing, and that's accurate. That is what's happening. And then the same thing from 1.5 to infinity. So from here over, I'm decreasing. So it's good. It looks like we have a pretty accurate rough sketch here. And that's pretty neat. We have 4 x-intercepts then. So 4 x-intercepts. And they are at -2, -1, 1, and 2. I also have 3 turning points. And they are roughly then at -1.5. Oh, no parenthesis here because I'm just listing my x values for this. -1.5, 0, and then +1.5. The next thing we should point out here is I know my degree. I know a little bit about my degree, at least. I don't know everything about it, but I do know that it must be an even number, and that's because both of my ends go in the same direction. I also know my leading, that's not how I spell leading, my leading coefficient must be a negative number. And that's because both sides are opening down. All right, I believe that is it, folks. Let's check. It is, and because that's it, I have to say goodbye to all of you. But make sure you subscribe to this channel, hit that bell so you can get notifications. And of course, hope all of you have a phenomenal day. Don't do drugs, and do your math carefully and with enthusiasm. Bye, everybody.